Welcome to this explainer. We are diving right into the foundational building blocks of thermodynamics today, and we're going to explicitly decode the fundamental laws that govern energy and heat. So think about a freezing winter day. You're outside, you're shivering, and you instinctively start rubbing your hands together, right? But how exactly does that mechanical work, the physical act of rubbing, actually produce warmth? It's a super relatable question, but it totally stumped early scientists. And honestly, it's the absolute perfect entry point into the laws governing thermal energy. Real quick, here is our roadmap for today. We've got 6 parts. 1, from caloric to energy. 2, the zeroth law. 3, heat, work, and internal energy. 4, the first law. 5, variables and specific heat. And finally, 6, processes of thermodynamics. All right, let's jump straight into section 1, from caloric to energy. Back before thermodynamics was a formalized science, folks actually believed heat was an invisible fluid. They called it caloric. The idea was that it filled the pores of objects and just kind of float around, like water running downhill from a hot object to a cold one. But enter Benjamin Thompson in 1798. This guy was boring a brass cannon, literally drilling out the metal barrel, and he noticed the sheer, massive amount of heat generated by the drill. Now here's the game changer. He saw that the heat depended entirely on the continuous work done by the horses turning the drill, not on how sharp the drill was. If the caloric theory was right, a sharper tool should just scoop out more of that fluid, right? But that wasn't happening at all. He mathematically proved that physical work literally converts to heat. It totally shattered the old theories and gave us the modern concept that heat is actually a form of energy. Moving right along, section 2, the zeroth law. Okay, imagine 2 gases in completely separate containers. If you bring them together, separated only by a wall that conducts heat, eventually, things are going to settle down. That settled state, that's what we call thermal equilibrium. It basically means the large-scale macroscopic variables of a system, stuff like pressure, volume, mass, have totally stopped changing over time. The temperatures between the 2 systems have completely equalized. And that brings us to the brilliantly named zeroth law. It was formulated by R.H. Fowler way back in 1931, and yeah, that was long after the first and second laws were already established, which is why they kind of had to awkwardly backtrack and call it the zeroth law. Anyway, it states that 2 systems in thermal equilibrium with a third system separately are in thermal equilibrium with each other. Now, I know what you're thinking. That sounds like basic logic, right? If A equals C and B equals C, well then A obviously equals B. But in the world of physics, this is actually profound. It is the absolute bedrock foundation that proves temperature exists as a universal, measurable property. Without the zeroth law, we literally couldn't build thermometers or standardized temperature scales. All right, let's get into section 3, heat, work, and internal energy. Now, we need to do a little bit of scientific myth-busting here because we really have to distinguish between heat and internal energy. In everyday conversation, we mix these up all the time, but in physics, heat is strictly energy in transit. It only exists when energy is actively moving from a hotter object to a colder one because of a temperature difference. You literally cannot say a system has heat. That's a huge misconception. What a system does have is internal energy. Internal energy is a state variable. It's the actual quantifiable sum of all the molecular, kinetic, and potential energies locked away inside that system at any given moment. So the golden rule to remember here, heat is the transfer, internal energy is what's actually in the box. Okay, with our definitions perfectly locked in, section 4, the first law. The first law of thermodynamics gives us a beautifully elegant mathematical equation, delta Q equals delta U plus delta W. This is really just the universe's general law of conservation of energy, specifically applied to our thermodynamic systems. It simply states that the heat you supply to a system, that's your delta Q, goes partly into changing its internal energy, the delta U. And then whatever energy is left over goes into doing work on its environment, the delta W. It's basically nature's perfect mathematical balancing act. You can't get something from nothing. To actually show this balancing act in action, let's look at the latent heat of water, which is 2256 joules per gram. So when just 1 single gram of liquid water boils and turns into vapor, it has to absorb 2256 joules of heat. But when you actually run the math to see how much physical work that water does by expanding into steam against the pressure of the atmosphere, it's only about 169 joules. Think about that for a second. That means the vast majority of that energy, over 2,000 joules, goes straight into increasing the water's internal energy. It's working to break those molecular bonds apart, not just expanding its physical volume. Which leads us perfectly into Section 5, variables and specific heat. Because thermodynamics is a macroscopic science, we have to classify our variables in two distinct ways just to make sense of the math. First, we have extensive variables. These indicate the literal size of the system. Think about things like internal energy, volume, or mass. If you take a system and literally cut it in half, well, those values get halved right along with it. Then, on the flip side, we have intensive variables. Things like pressure, temperature, and density. If you cut that same system in half, the temperature of each individual half stays exactly the same, right? Keeping these straight is an absolute must for checking the consistency of your thermodynamic equations. And that brings us to a super useful intensive variable, specific heat capacity. This is basically just a fancy, precise way of measuring exactly how much energy a very specific material needs to warm up by 1 unit of temperature, completely independent of how much actual mass you're dealing with. If you've ever been cooking and wondered why your metal pan gets burning hot in seconds while the water sitting inside it is still barely lukewarm, well, specific heat capacity is your answer. Water takes a ton of energy to heat up compared to metal. Now, when we look at the data for molar-specific heat across a few different solids at room temperature, it really shows you how beautifully predictable nature can be. According to the principle of equal partition of energy, we predict this value should be around 3 times the universal gas constant, or roughly 25 joules per mole Kelvin. And look at the numbers. Aluminum, copper, lead, silver, tungsten, they all line up perfectly right around that 24 to 26 mark. It is always so satisfying when experimental data just perfectly nails theoretical physics. But of course, notice carbon sitting there at 6.1. It's a notable exception, and it's a great reminder of where these general rules kind of hit their limits. Finally, let's look at Section 6, Processes of Thermodynamics. Before we can dive into messy, real-world constraints, we actually have to imagine an idealized baseline. In physics, we call this a quasi-static process. Basically, it's a completely hypothetical, infinitely slow process. Imagine a gas expanding so incredibly, agonizingly slowly that at every single stage of the expansion, the system remains in perfect thermal and mechanical equilibrium with its surroundings. Now, obviously, this is a purely theoretical construct. Nothing in the real world works quite like this, but we absolutely have to have it as a baseline to cleanly apply our mathematical formulas. So using that idealized quasi-static model, we can basically categorize all thermodynamic processes into 4 strict constraints. First up, isothermal, where we lock down the temperature so it stays perfectly constant. Second is adiabatic, meaning the system is completely insulated. Literally no heat flows in or out. Third is isochoric, where the volume is locked firmly in place. And finally, isobaric, where the pressure is held constant. By simply deciding which of these variables we're going to lock down, we can predict exactly how the first law is going to distribute the work, the heat, and the internal energy. Okay, so we've mastered the first law. We know the rules of energy conservation. But this leaves us with an incredibly provocative question, one that draws on the famous Kelvin, Planck, and Clausius statements, and really makes us wonder about the ultimate limitations of nature. Is it actually possible to build a process whose sole result is completely converting heat into work? Or how about an engine that literally just moves heat from a cold object to a hot one with no other changes? Here's the catch. The first law only says energy must be conserved. It doesn't actually forbid these perfectly efficient machines. Yet the real world tells us we can't build a perfectly efficient engine, and heat absolutely never flows backward from cold to hot on its own. So what invisible rule of nature is stopping us? Well, that mystery sets the absolute perfect stage for the second law of thermodynamics. Thanks so much for joining me on this explainer, and keep questioning the physics around you.